Let's take a look at lesson 18 together here in Unit 6. We're modeling some circular motion. We're coming to the end of our unit, so this is where we start putting it into some different interesting applications and some ideas that would go about why we care about the unit circle. Our warm-up is comparing bicycles. So each graph shows the vertical position v in inches of a point on the outside of a bike wheel, s seconds after the wheel begins to spin. So after 1 second, one wheel, this blue one, has gone through that, whereas the black one has gone through that. Okay, so we have two different wheels going on. And if you just need that kind of picture, here's a wheel, here's a bunch of spokes on it, not spikes. And we're looking at a wheel like this, and we're looking at the vertical position off the ground. Okay. Which bike has larger wheels? Explain how you know. Well, I know that bike A has the larger wheels. And I know that because it has a larger difference going from its minimum to its maximum. See how both of them are hitting the ground here at 0? Graph B only has a wheel that's about 20 inches because it tells me that V is in inches. So graph B, right here in the middle, has a total height of 20 inches because that wheel would spin up to 20 and down to 0 and up to 20 and down to 0. Whereas graph A goes up to like 26, maybe. Looks like 26-inch wheels. So it, again, hits the ground down here, but it gets all the way up to 26. So I know that because it has a larger amplitude. Let's use some mathy terms. Larger amplitude. It has an amplitude of 13. Please remember it's half of the total height, so if it's going from 0 to 26, its amplitude is 13, so it's got maybe a radius of 13. Whereas graph B has an amplitude of 10. Which bike's wheels are spinning faster? This might make some sense to you if you're thinking if it's a smaller wheel for the same amount of time. You know, maybe it's spinning faster. And it is. When we're thinking about which one is spinning more, this one has gone through a full rotation by the time it gets here at about 0.25 seconds. It goes through 3.5 rotations. So graph B is spinning faster because it went through 1, 2, 3.5 rotations per second. And I could compare that to graph A that is going through, starting here and going through 1, 2.5 rotations per second. So, nice way that we can kind of look at this and model some tires on bike wheels. Let's take a look now at another application, 18.2, around a carousel. Jada, Noah, and Elena are riding around a carousel. Here's a view from the top. I'm smiling to myself because I can already tell if you are in block 2, you are already making my connection for carousels right now. Sorry. Okay. Inside joke. The carousel moves in a counterclockwise direction, so it's going this way. When the ride begins, Jada is at position J, Noah's at N, Elena at E. The measure of angle JON is pi over 2. The measure of angle NOE is 2 pi over 3. Now I'm putting that there like that because right now I'm already starting to think that I'm going to probably need my nifty unit circle. But also, notice that is from N to O to E, not from J-O-E. Okay, so what we need to do is actually be adding pi over 2 and 2 pi over 3. And maybe you're already seeing what that might be, right? So if we go 2 pi over 3 and then another pi over 2, another quarter circle, we're looking here at 7 pi over 6. So I'm going to label what that point is 7 pi over 6. So the radius of the carousel is 20 feet. How far does Jada travel to reach Noah's starting position? It's asking, what is this arc length? And we've seen that before because it's a portion of the full circle, the circumference going on. So we want to think about maybe the full circumference of the circle. And she hasn't gone that full circumference yet. She's only gone a portion of that circle. So we're going to set that up, right? A circumference of a circle, you may remember from geometry, is 2 pi times the radius. We know that now from the unit circle because one time around the circle when the radius is 1, the unit circle, the circumference is 2 pi times 1, or just 2 pi. Right? That's what radians are. There we go. We're right back to that idea about what the definition of a radian is. So if circumference is 2 pi times radius, and this radius is 20 feet, that's how much distance she would travel around the whole outside, but she hasn't gone the whole outside. She's only gone a quarter of a circle. So we want 1/4 of 2 pi times 20. Well, 2 times 20 is 40, and 40 divided by 4 is 10 pi, and maybe you want to estimate that as instead of 3.14 we need 10 times as much, 31.4-ish feet. And this time to get to Elena's starting position, we still want to take that full circle of 2 pi times 20, and instead of just a quarter of it, we want a little bit more than half of it. In fact, we want a half plus another sixth. Okay, so she's gone 1/6, 2/6, 3/6. Wait, let me go that again. We want sixths. Right, I can't say 7/6 because that was taking us all the way to 2 pi, right? But if we're looking at this angle here, 7 pi over 6, well, let's see. Yeah, she's done half of that circle here. So splitting that up into sixths, that would be 12ths of the full circle. That's what I'm looking for. Had to do a little bit of reasoning there. Okay. So if I split this up into what portion of a circle has she been through, those nice even equal angles that we have there means we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 equal pieces, and she has gone through 6. She's gone through 7 of those 12 pieces. So she's gone through 7/12 of a full circle. So again, 2 times 20 is 40. 40 times 7 divided by 12. Ugh, that's such an ugly number. She's gone through 280 twelfths of pi. We can do better than that. 40 over 6 pi. 70 over 3 pi. Right. Or we could just estimate it at about 73.3 feet. So that makes sense. She went more than double from Noah's spot to Elena's spot. If the carousel makes one complete rotation every 10 seconds, at what times would she be back at her starting position? She'd be back at her own starting position at 10 seconds, and then at 20 seconds, and at 30 seconds, and at 40 seconds, until the end of the ride. At which times would she be at Noah's starting position? Okay. Well, the first time she's going to be at Noah's starting position is again at a quarter of the time around the circle. So the first time she would be at Noah's starting position would be the 10 seconds for a full rotation divided by 4, because she's only gone a fourth of the way of that 10 seconds. Okay, so just like we took a fourth of the circumference here, we're going to take a fourth of the time here. So she'd be there at like 2.5 seconds. Oops, sorry about that. Finish. Let me get back here. There we go. So she'd be there at 2.5 seconds. And again, once she's there at 2.5 seconds, it takes her 10 seconds to get around the circle, again, around the carousel. So she'd also be there at 12.5 seconds. And at 22.5 seconds. And at 32.5 seconds. Every 10 seconds she's going to be back at that same place. And so that would keep on going too until the end of the ride. We got one more question. Don't quit on me yet. Number 3. Now the ride lasts for 3.25 minutes. Where will she be when the ride ends, and how far will she have traveled? Whew. All right. First thing I'm going to do is convert minutes to seconds. So I need that information. 3.25 minutes times 60 seconds per minute. Oop, let's try that again, and this time actually multiply it by 60. So she has gone around and around and around for 195 seconds. Okay, so in 10-second intervals, this means she has gone through 19 and a half rotations. It takes her 10 seconds to go around one time. Okay, so she's gone around 19 times and another halfway around, because it's only 5 more seconds, not 10 full seconds all the way around. So she's gone 19 and a half rotations. Okay, so from here, when she's gone 19 and a half rotations, where will she be at the end of the ride? I'm just going to draw a little picture of this. Right, here's that unit circle. She's going to be right here, because she started here. Oh wait, Elena. How far is Elena? Where's Elena going to be? Sorry, let me change colors. Thank goodness I read that. Because Elena started the ride here. And so she is now going 19 and a half rotations from there. She's going to end the ride here. And she's going to end that at pi over 6. Just directly across the unit circle. So she started here at 7 pi over 6. She's going to end here at pi over 6 directly across. Now she's gone 19 and a half rotations. Last question we need is, how far has she traveled? We already calculated before that distance around the full circumference. Remember circumference right there that's happening. And that circumference was 2 pi r. So circumference, 2 pi times the radius of 20. And she's gone that distance 19 and a half times. So I'm going to times it by 19 and a half. I could do this in terms of pi, but I'm just going to do some straight multiplication here. So 19.5 times 2 pi times 20 tells me that she has gone 2,450.44 feet.